Hello. All right, let's talk about cephalopods. Here we go. There are two extant groups. One are going to be the nautiloids, and the chambered nautilus is going to be our chief representative there. And on the other group, they're going to be the coleoids, and so that's a group that includes octopus as well as things like squid. Um, there are a bunch of extinct groups also within the cephalopods, and these are some of the best fossils out there. People really like them anyway. So you've got your ammonites, which is this particular group, and a bunch of related organisms that are very similar to ammonites. They're going to be called the ammonoids. And I'll show you how we distinguish these a little bit later in the talk. It's by the position of a thing called the siphuncle, but you don't know what that is now, so give me a minute. Yeah. Belemnites leave a lot of fossils as well. The ammonites and belemnites are very common in the Cretaceous of Texas, for example. And also over in the UK, the whole Jurassic coast, they call it, just loaded with these sorts of things. Belemnites are going to look like a very large caliber bullet slug. They're kind of shaped like that, and these are going to be internal. They're essentially a covering around the ink sac of these animals. Internal in the body, the way a cuttlefish pen is internal inside of its body. And then you go back to the very early ones. You've got both straight-shelled nautiloids. That's how they started out. Straight-shelled things like ammonoids. That's how they started out. And you've got the very earliest ones. And those are going to have a little shell. It's kind of wide and a little bit tall like that, sometimes a little bit curved, and it works just like the other ones. So the shell in these creatures, when they have a shell, an external shell, is going to serve to regulate their height in the water column. And you do that the same way a submarine does it, or kind of the same way a diver does it. You add weight and displace air, or, vice versa. And so what they're going to do is there are a series, or rather the shell's divided up into, let's say, two main parts. The body chamber is going to be kind of fragile, at least in fossils, but this is just one big cup, and this is where the animal itself, like the meat of the animal, is mostly going to stay. There's just one little part of the animal that's actually going to run all the way through all of these other chambers. These chambers are going to be empty, but can be filled with water. It's able to pull in water from the junctions between the chambers. So the more elaborate those walls become, the sort of wavier the surface of the suture becomes, the more surface area there is to bring water in. And so it makes you potentially faster at flooding the shell. And flooding the shell is going to make these things dive. So they can flood the shell very quickly, which means they're going to be pounce predators. They're going to be up above, and something's going to be swimming along, and they can flood their shell and then, boom, drop right down on it. That's how they work, we think, for most of the old ones. And then the problem is, so you drop down, and now you've flooded your chambers, and so what do? There is it's like a vein. It's the siphuncle, and it's going to run down each of these chambers. It goes through a hole in the center of each chamber. So one way that you can tell a cephalopod shell is that there has to be a hole in the center of every single one of those chambers, because that's where the siphuncle went. And then the position of that siphuncle is going to tell you what kind of cephalopod you're dealing with. For example, ammonites are going to have that siphuncle right near the surface on the outside, so it'll be right here. In Nautilus, it's pretty close to the center of each chamber, and so it's going to run right down here. And so if you just see a little fragment of one of these, you can tell right away. It's pretty easy, yeah. And so the siphuncle is filled with extremely salty liquid, and that is going to pull the water out of these chambers, because the seawater is less salty than this thing, which means that just through osmosis, it's going to enter into the siphuncle, and then it can be expelled by the creature. And so it's kind of a slow draining process because it's osmotic draining, but a very fast filling process. And frankly, once you've pounced on something, you're either eating for a while, or it'll take a while for these to recover, potentially. Yeah. All right. And here are some things. So there are different mechanisms of or methods of coiling. They can be endogastric or exogastric. If you see that in the description, here's what it means. Endogastric means that the siphuncle and the digestive parts are basically going to be on the inside of the curve. So it's like the stomach parts are on the inside of the curve. Whereas this would be exogastric curving. It's just the opposite. The siphuncle holes, you can see them right here, are going to be on the outside of the curve. Most of them are curved to some extent. Even the ones that are relatively straight. Sometimes if you look at the earliest growth part, there will be a bit of a curve there. These things right now mostly just look like cylinders. Some of them are very beautiful cylinders. They'll still have some of the mother of pearl that was in there. But back then they had color patterns. And so this is from the Treatise on Invertebrate Paleontology. These are some of the color patterns that have been found intact on some of these cephalopod shell fossils. And so, yeah, you got linear ornaments. That looks pretty good. Zigzags. Wow. Yeah. Little stripes in there, little corkscrew sort of things. Yeah, looks good. Great big W down there at the bottom. I don't know what that's for. So here's a little bit about siphuncle position and just how it varies. These are some of the earliest growth stages. So the earliest part of the shell is called the protoconch, which we've got written right here, Protoconch. And so the protoconchs of the different major groups of these shelled cephalopods are going to have different appearance and a different position of the siphuncle, either endogastric, exogastric. What do the little chambers look like? Are they partial chambers? Or are they more complete chambers? Or do they have complex sort of patterns? Is there like a branching siphuncle apparently? Or maybe those are little patches where water can get in between the chambers so that they can get it out more efficiently? I don't know. Yeah. But here you can see the chambered nautilus. This is sliced in half. This is this guy up here. Yeah, RIP. And look right there, dead center of each chamber. That's the siphuncle. There you go. So that's it. All right, now you're oriented. So if you were to take one of these big, beautiful beauties and look inside of it, what would you see? Obviously, don't do this. They're rare. They're awesome. Yeah, be nice to nautiluses. Here's the siphuncular cord. So this is going to actually extend throughout the shell. At least throughout the parts of the shell that it wants to be able to fill and drain regularly. The stomach and intestine and gonads are all tucked away back here. There's a gill that's kind of on the bottom, and it's going to pull in water and then expel water, and part of breathing and moving are kind of connected in this way. This is more of like a side-to-side movement. With the up and down movement being at least partly through flooding the shell, like buoyancy control. They are, many of them are going to have beaks they can use to sort of snap creatures to pieces, kind of like the beak you would find in an octopus, for example, or squids. Squids have nice beaks, yeah. Here is some soft tissue preservation because that's what we're all about here in this class. In this one, the eyes look like they did not do particularly well. And this is just an ultraviolet photograph, so it's picking out some things, but if they went in there with Raman spectroscopy, I wonder if they could get a signature from melanin from those black dots that are in the area where the eye would have been. But who knows? This is something like a vampire squid. I believe this was a belemnite, although we'd have to look at the paper to be absolutely sure. But look at those little hooks. These would be on the tentacles. And the neat thing here is that there are very large sort of nerve bundles that are going to innervate each of the tentacles. And you can actually see the big, thick nerve cords. So those managed to survive fossilization here. And also in this one, so here's another little individual. There you can see its little ink sac up there. And a little bit of the ink duct just on the fossil where it split open. Here you can see the nice little spines on some of those tentacles, and yeah, evidence of some of the nerves actually got preserved. These are very tough, durable, robust nerves. So it's not necessarily completely out of the question, although it's pretty awesome when it happens. Here's another one. We've got a little preservation of the eye here, and we do have some of the axial nerves actually with a little bit of organic material plus diagenesis still around. So there you go. Yeah. Arm brains. That's a dumb way to say it, but yeah, it's the title of their paper, and it's an awesome paper. So, all right, maybe I'm dumb for thinking it's dumb. Yeah, that's fine. It's pretty cool. All right, here are the nautiloids. Yeah, for the most part, yeah, entirely. All right, so these are the early branches, and the earliest ones tend to have straight shells. And so they're holding them up like this, and I think that makes a lot of sense in terms of buoyancy. Yeah, you'll see them often drawn, like kind of moving sideways, and I guess that could work once they are neutrally buoyant, but I would have thought that this sort of position would be much better, at least for getting ready to eat. And, you know, who says they had to stay in the same position all the time? That would get boring. But you get these straight ones, you get real differences in the siphuncle. Like, look at this guy. He's got giant, wide, sort of siphuncular holes through those chambers. Which potentially allowed faster pumping out, so a faster recovery after a miss or a hit. And then back here you get the really early ones. You can see what those look like. Basically, curving only. There's a little experimentation with curving, both endogastric and exogastric. But the real sort of curving only happens in groups related to this. All right. Here we have some. So let's talk about ammonoids now. We'll put the nautiloids away, things like Nautilus and all its friends. Talk ammonoids. Here are a bunch of different ammonoids. This thing looks like a gastropod, but it's massive. It's actually the shell of a cephalopod. Yeah, crazy as that seems. Same with this one. These are some early ones where it looks like it's transitional between the sort of straight shell and the curled shell. They're just not particularly well curled yet. It is thought, and this may change over time, but it's thought right now that the ones with the shells that are not bilaterally symmetrical are likely to have lived their lives mostly along the bottom, although that may change because this is a diverse group of mostly sort of high energy predators. So, what you do see, though, as time goes on and in the different groups, is a change in the sutures. So that's where the different chambers come together. So here you can see the chambers coming together and see how they have a little zigzag right here. Zigzag, zigzag, zigzag. In a nautilus, those are basically just smooth lines. They may bend a little bit like that, but they don't really do anything in all the nautiloids. So nautiloids have straight line chambers with a siphuncle right through the middle. Ammonoids have a siphuncle right on the outside, and they have increasingly interesting suture lines. So some of the early ones were this group called goniatites, and these are in the Paleozoic, I believe, exclusively. And they have sort of zigzag patterns, just like this. Then, also developing during the late Paleozoic and carrying on into the Mesozoic, you have ceratites. And so these are going to have curved sutures, but they're going to have little zigzags here. So they're building up a little bit of extra surface area. And then once you get to ammonites, some of the early ones are relatively simple, but they get increasingly complex. This is the join between two chambers. And it's actually the same pattern every single chamber as you go along. They're really nice to look at. They're just something. Yeah. And so the more area you have, basically, the more length of that line between the chambers, the faster you can bring in water when it's time to dive. And so these are adaptations toward becoming, going from just pretty good predator to like hyper predator. And these were very common in times when there are lots of fish and other animals to pounce on. These do very well. And in times like with extinctions that hit their prey populations, these things go extinct. We'll get to that later, though. So, as far back as the Devonian, you actually get some of these, some of this transition from straight-shelled ammonoid to curly-shelled, and then you get sort of an evolution. Starts to split, but they look relatively similar here. And yeah, over time you get more tightly coiled whorls. The whorls coil on top of themselves, which you can see here. It's kind of outside, but it's kind of wrapped around itself here. Look, you can't see the earlier rungs, whereas here you can see right down to when it was a little tiny baby. And this one is covered up. So that's a later adaptation. We'll get into why in a moment. Here's that moment. So the idea is that over time, the body size of the animals increases. And with an increased body size, you're going to have higher metabolic requirements, but also you can potentially do more. You can move more forcefully, may make you better at diving, may make you better at draining chambers. Yeah, hard to say. But what you see is that as time goes on, the relative proportion of the sort of body chamber tends to go up. And so there's a couple ways that they can do this. They can increase the height of the body chamber. So here we go. We're increasing the height of each whorl. They can increase the width of each whorl, and you can pack more meat in there if you get wider faster. Or you can increase the length of the body chamber. Just start it further back and have it go further around. And then the phragmocone will be everything that is inside of that. Yeah. And honestly, all of those work. All right. So this is last little bit. It's kind of a sad ending, but ammonites have a sad ending, so I don't know. That's not my fault. Don't blame me. This is from a study where they actually looked at the ratio of metabolic to environmental carbon. So these are creatures that are going to make a calcium carbonate shell. And if that carbonate comes from plants originally, plants are quite selective in the ratio of C12 to C13 that they bring in. So they can tell the difference between isotopes of carbon. And it's the Rubisco enzyme in plants. This is the one that does carbon fixation, essentially, that is responsible for discriminating between the different isotopes. Plants are selecting and enriching a particular isotope of carbon. And then if something eats the plants and then something eats the thing that ate the plants, then they are going to end up picking up this sort of metabolic carbon, which is going to have a real bias compared to the carbon just in CO2 in the atmosphere, or the carbon that's dissolved into the water. Yeah, it's going to be a little different. And so they're able to measure the ratio of like the carbon in the shells of these animals, some of which will come from diet, and some of which will come from the environment. And basically, here's the situation. So they're looking at extant nautiloids, and here are two of the species, and they have a very low percentage of metabolic carbon, which is an indicator in this case of a very low metabolism. They don't eat much, and they don't need to eat much. So most of their carbon in their shell is actually just coming from the seawater because they're not eating enough to do that. So they're extremely low energy, which would mean that in times when bad things happen to your food population, they would potentially have a greater survival chance. Compare that to octopus, like the argonaut that has an egg case, much higher metabolic rate. Compare that to just a bunch of sort of squids and things, and yeah, they're generally relatively high metabolic rate. The cool thing is you don't have to just do this with extant animals. You see where this is going? You could do it with the fossils too. You could look at the carbon ratios in some of these fossils. So here we have a nautiloid, and here we have an ammonoid. And so compare. These are from the same time and the same place. So they're in the same ocean and they're exposed to the same water. And look at that. The ammonoid has its high variability, but really high metabolism rate, basically, because a lot of their shell is made of this metabolic carbon. Yeah. Compared to the Nautilus, which then and now just, ugh, yeah, just can't in the morning, can't anytime. Here's another nautiloid for comparison. Different time and place, but the same as these ammonoids. And look at the ammonoids, much higher. And so this is the idea that when there was an extinction that affected the rest of the ecosystem, ammonoids have a high metabolism, so a high need for constant food, or else they die, basically. And when those food sources are perturbed by something like the Chicxulub event, which is the big comet thing, whatever you want to call it, hitting the Earth and wiping out the dinosaurs, which we will get to, then basically they're the ones that suffer the most. The ammonoid or the nautiloid is going to be the most tolerant of decrease in food supply. It can do more with less. Yeah, although it doesn't really do much, as you can see up here. Just moves around a little bit. They're adorable. Honestly, I'd love to have one as a pet. All right, there you go. That has been cephalopods. I hope that was illuminating. They are good fossils.